So let's start discussing. We are discussing catalyst and reagents. In this, today's discussion will be focusing on hydride reducing agents. These are the compounds which transfer hydride ion, okay, to the functional group or to reduce the reactant. Here, the external source of hydrogen is not required. The reagent has one or more hydride ions in it, and it is transferred to the reactant and carried out the reduction processes. There are three types of hydride reducing agents which we are going to discuss. First of that is lithium aluminum hydride, LiAlH4, also commonly represented as LaH. This is the structure for lithium aluminum hydride. Here you can see aluminum is attached to four hydrogens, rather we can say hydrides, okay? And then this lithium is having positive charge. Okay? It's a salt. It is very strong hydride reducing agent. Normally it is a white solid. If impure, it is looks like a gray colored solid. LH is mostly insoluble in organic solvents. And whenever it is added in the reaction, the solvents preferred are dry ether and dry THF, okay, which makes the suspension of this lithium aluminum hydride in these solvents. This LAH is highly sensitive to air and moisture. It is inflammable. It readily catches fire when it is exposed to the air or comes in contact with the water. It reacts violently. It is used for the reduction of polar unsaturated groups like carbonyl compounds, nitriles, imines, nitroso compound, nitro group, etc. At the same time, non-polar functional groups or non-polar unsaturated groups like alkenes, alkynes, they remain unaffected. Being very strong reducing agent, it reduces most of the groups present in the reactant. So the selectivity decreases. We can say it is non-chemoselective. Now let's discuss few reactions of LH. LH used for the reduction of aldehydes and ketone. When it is used for the reduction of aldehydes and ketones, it gives corresponding alcohols. Aldehyde, as we can see in this reaction, is converted into a primary alcohol, whereas ketone is reduced to secondary alcohol. When we have two functional groups like carbon-carbon double bond and an aldehyde, okay, as we said, LH selectively reduces polar unsaturated functional groups. So only the aldehyde group is get reduced to the primary alcohol. So here in this last example, we can see the selective reduction of aldehyde in presence of carbon-carbon double bond. Next, use of LH for the reduction of acid and acid derivatives. Acids, carboxylic acids particularly, easily get reduced to the primary alcohol with the LH. Acid halides or acid chlorides treated with LH and reduced to the primary alcohol. Also, amides are reduced to primary amines by LH. Few more acid derivatives like acid anhydride get reduced to primary alcohol. Also, esters can be easily reduced to primary alcohol by using LH acid derivatives. Next, use of LH for the reduction of nitriles. Nitriles will be reduced to the primary amines, whereas the nitro compounds reduced to primary amines using LH. So these are the few functional groups, polar unsaturated functional groups reduced by lithium aluminum hydride to the corresponding products. Next hydride reducing agent is radon. The structure you can see here, where aluminium is having two hydride ions, can be donated. The reactivity of radon is very similar to lithium aluminum hydride, but it is more stable to air and moisture when we compare with LH. Rather, radon is available as 70% solution in toluene. So here, radon is having advantage of handling as compared to lithium aluminum hydride. Okay. So we can handle radon easily as compared to LH. This radon is thermally very stable as compared to LH. It is stable up to 200 degree Celsius. Next, we are going to discuss sodium borohydride, the third hydride reducing agent. Structure is like this, where we have boron attached to the four hydride ions, and it is a salt or sodium salt of it. This NaBH4 is used as a hydride reducing agent, but it is less reactive as compared to LH or radon. And that means the chemoselectivity is more when we compare NaBH4 with lithium aluminum hydride. It is soluble in polar organic solvents like methanol, but it is insoluble in non-polar solvents. This sodium borohydride is used for the reduction of aldehydes and ketones in presence of ester, nitriles or nitro groups. So when we say the sodium borohydride is chemoselective as compared to lithium aluminum hydride, here we can see aldehydes and ketones can be reduced to corresponding alcohols, even if the esters, nitriles, and nitro groups remain unaffected in the reaction process. Also, the non-polar unsaturated groups like carbon-carbon double bond and carbon-carbon triple bond, alkenes and alkynes remain unaffected. Now let's discuss few examples. Use of sodium borohydride for the reduction of aldehydes and ketones. Aldehydes readily get reduced into primary alcohols, whereas ketones reduce to the secondary alcohol. Discussing selectivity in reduction of aldehydes and ketones in presence of other polar functional groups. Here we can see aldehyde can be reduced to primary alcohol in presence of carbon-carbon double bond. Also, in this example, the aldehyde is reduced to primary alcohol, keeping this nitrile group unaffected. So, sodium borohydride selectively reduces aldehyde into primary alcohol. The nitrile groups remain unreacted or unaffected in the reaction. Sodium borohydride can also be used to carry out reduction of aldehydes in presence of nitro group. So here we can see the nitro group remain unaffected and aldehyde is get reduced to primary alcohol. And ketones or aldehydes also can be reduced in presence of esters. Here in this example, this keto group is reduced to secondary alcohol, keeping the ester unaffected.